Hello everyone, and welcome to the Lab Water Source, an interactive webinar series where we wade through everything from the fundamentals of buying and maintaining a laboratory water purification system to ensuring the water meets your application needs. I am your host, Lauren Armstrong, and today's presentation is Myths and Truths of pH and Conductivity of Ultrapure Water. Today's webinar will have two presenters. Knepper is the Global Application Specialist for Water Purification at Thermo Fisher Scientific. Kim previously served as Technical Product and Sales Support for the Barnstead Water Purification Solutions. Today, Kim works with teams to develop training programs and perform application testing and analysis. Kim holds a Bachelor of Science degree with a major in biology. Gayle Gleichauf is the Applications Lab Manager for Thermo Fisher Scientific Water and Laboratory Products. Gayle has over 25 years of experience with analytical testing, ranging from field testing and simple screening to stringent regulated analytical determinations. She will be your host for the first portion of this webinar and will share with you her experiences in testing ultrapure water. As a registered guest, you will receive a link to this recorded webinar in your email when it becomes available. This webinar, including Q&A, will last about an hour. Type your questions at any time into the text box in the Q&A module that you see on the right side of the screen. Our presenters will answer questions at the end of the webinar. This webinar is interactive, and you'll be asked a few survey questions throughout the presentation. We will share the results so you can compare your answer with your peers. This ends our introduction, so without further delay, I present to you Gayle Gleichauf.
Thank you, Lauren. Greetings, everyone. Thanks for joining us today. There are a number of myths about the measurement of pure water. Ultrapure water is not a natural state. Therefore, verifying its quality outside of the water system requires some important considerations to understand the results. Today's webinar will explore the myths of pure water measurement and define how to properly measure the conductivity and pH of ultrapure water. We will also review how ultrapure water systems purify the water and how impurities are measured. Today, we will bust the following myths. Myth number 1. Ultrapure water conductivity after dispensing should match the ultrapure water system display. Myth number 2. The pH of ultrapure water should be 7.0. Myth number 3. The ultrapure water system display measures all the impurities in water. And myth number 4. Accessories added to the ultrapure water system will always improve conductivity resistivity. Let's dive right in with our first myth. Myth number 1. The ultrapure water conductivity after dispensing should match the ultrapure water system display. For instance, after collecting ultrapure water in a container, the ultrapure water should display 0.055 microsiemens per centimeter, or 18.2 megohm centimeters resistivity, and it should match the ultrapure water system display. Right? Well, there's more going on than we might realize. The truth is, ultrapure water immediately picks up carbon dioxide and conductivity upon dispensing. Dispensed ultrapure water will read higher than 0.55 microsiemens per centimeter upon dispensing and will climb rapidly to an equilibrium near 1 or 2 microsiemens per centimeter. If we're reading resistivity in megohm centimeters, dispensed ultrapure water will read lower than 18.2 upon dispensing and will drop rapidly to an equilibrium near 1 or a half of a megohm centimeter. We'll talk more about this shortly. And our second myth. After generating the ultrapure water, the pH should be exactly neutral pH 7.0. And this pH is easy to measure. But again, there's more going on here than we might realize. The truth is, ultrapure water can quickly decrease after it's been generated. The pH will quickly decrease. Fresh ultrapure water will read anywhere between pH 5 and 7, and the pH will drop with time. In addition, pH measurements of ultrapure water tend to be unstable, and they can be inaccurate due to the low ionic strength of ultrapure water. Let's move into our first survey question now.
Thank you, Gayle. Using the survey question module in the center of the screen, please answer the following question. What quality control measurements do you perform on your ultrapure water? Check all that apply. Just a quick reminder, if you have any questions, you can enter those using the Q&A module in the lower right corner of the screen. I'll give it another moment as answers are still coming in. Okay, I will now share the results and hand things back over to Gayle.
Thanks, Lauren. Well, it looks like most people are measuring conductivity, and many people are measuring pH. About a third of people are measuring TOC, and some are doing turbidity with some others in there. So thanks for those results. Good to know. All right, so what's going on with our pH and conductivity readings? Well, what we're seeing is the effect of carbon dioxide in the air dissolving into the ultrapure water. This tends to happen quickly, and when it does, the conductivity will rise to near 1 microsiemen per centimeter, or 1 megohm centimeter resistivity, and the pH will drop and typically settle near 5.7. Here is the equation that explains the process. When CO2 is in contact with the water, it dissolves into the water forming carbonic acid, which then dissociates to a certain extent to hydrogen ion and bicarbonate ion. It is these ions that cause the unexpected conductivity and pH readings, which we see in the ultrapure water after it has been dispensed. At typical pressure and 25 C, there will be about 400 milligrams per liter CO2 in ambient air. That causes the concentration of about 1 times 10 to the minus fifth molar of carbonic acid in ultrapure water, a conductivity near 1 microsiemen per centimeter, and a pH near 5.7. This chart shows us the effect of CO2 levels on the conductivity of ultrapure water. When there is no air and no CO2 in contact with the ultrapure water, the expected conductivity of the water is 0.055 microsiemens per centimeter, or 18.2 megohm centimeters resistivity. For outdoor or ambient air, 300 to 500 parts per million CO2 in the air is typical. When the ultrapure water is in contact with ambient air containing up to 500 parts per million CO2, the expected conductivity of the water rises to around 1 microsiemen per centimeter, or 1 megohm centimeters resistivity. Crowded rooms can reach 1,000 to 3,000 parts per million CO2 in the air. In that case, the expected conductivity can rise to around 2 microsiemens per centimeter, or 1/2 megohm centimeter resistivity. So what causes these varying CO2 levels? Factors include the season of the year, plant respiration, human respiration, decaying vegetation, ventilation in a room, and other factors. As these CO2 levels vary in the air, so does the CO2 level and the conductivity reading of our ultrapure water. This chart shows us the effect of CO2 levels on the pH of ultrapure water. At 25 C, when there's no air and no CO2 in the ultrapure water, we expect a pH at 7.0. When the ultrapure water is in contact with ambient air, containing around 300 or 500 parts per million CO2, the expected pH of the water drops to near 5.7. This means when air and CO2 dissolve into our ultrapure water, conductivity and the pH change. This is a well-understood phenomenon that we do expect to occur. We've seen how CO2 in air affects the conductivity reading in our ultrapure water. Now let's take a quick look at how the temperature of ultrapure water affects the conductivity. The effective temperature on ultrapure water is nonlinear, and the higher the temperature, the higher the conductivity. As we already know, at 25 C, we expect ultrapure water to read 0.055 microsiemens per centimeter, or 18.2 megohm centimeters resistivity. However, at 30 degrees C, we expect ultrapure water to read higher. It should read around 0.071 microsiemens per centimeter, or 14 megohm centimeters resistivity. While at 20 degrees C, we expect ultrapure water to read lower. It can read 0.042 microsiemens per centimeter, or 23.8 megohm centimeters resistivity. This means that when we measure the conductivity of our ultrapure water, we need to be aware of the temperature. We will want to record the temperature and consider using temperature compensation to adjust the reading to 25 C, depending on the criterion that we're comparing to. If we do choose to use temperature compensation, we will choose a nonlinear temperature correction that is suitable for ultrapure water. So let's look at some published criteria for purified water quality to see how the experts judge ultrapure water. The United States Pharmacopoeia publishes certain general chapters on water quality measurements. USP 645 conductivity of pure water is shown here in the first column. The American Society for Testing and Materials publishes a second standard called D1193 for reagent water quality. The highest quality water, type 1, is shown in the middle column, and the lowest quality of purified water, type 4, is shown in the last column. Note that the conductivity or resistivity is a criterion for each one of these pure water standards. TOC is a criterion for the purest waters, the USP and ASTM type 1. But pH is not a criterion for the purest waters, and when it is specified for type 4 water, the range is quite broad. Anywhere between pH 5 and pH 8 is to be expected. Looking more carefully at USP 645, we see that a conductivity reading of up to 1.3 microsiemens per centimeter at 25 C will pass the stage 1 criterion for purified water. This corresponds to the values that we recently looked at, where we expect a conductivity reading near 1 microsiemen per centimeter when ultrapure water equilibrates with CO2 and air. This is a measurement that can be done by collecting a grab sample of the water and measuring it with a dip-type conductivity probe. For ASTM D1193 type 1 water, we see that the criterion for a passing conductivity measurement is 0.055 microsiemens per centimeter, or 18 megohm centimeters. This is the value that we would expect to read when water is not in contact with air. This is a measurement that will need to be done by measuring conductivity in a flow cell that prevents the ultrapure water from contact with the air. Finally, we see that the pH of the ultrapure water is not a critical criterion for the USP pure water specification or the ASTM type water reagent specification. For the ASTM type 4 reagent water spec, a wide range for pH is specified. To wrap up this slide, note that pH is not a sensitive indicator of ultrapure water quality, so specifications may not even include pH measurements. pH of ultrapure water is not expected to be exactly 7.0. If ultrapure water conductivity meets specifications, pH will be within an expected range, so we may not even need to measure it. In the previous slide, we talked a little about making conductivity measurements, whether by grab sampling or by flow cell measurements. In this slide, we can get into some detail on measuring the conductivity of ultrapure water. We have two basic options. We can collect and measure a grab sample, or we can make the measurement in a flow cell. If we collect and measure a grab sample, the ultrapure water will absorb CO2 from the air. The conductivity will be greater than 0.055 microsiemens per centimeter, and less than 18.2 megohm centimeters resistivity. For example, if I use USP 645 as my ultrapure water spec, the conductivity of my grab sample can be up to 1.3 microsiemens per centimeter at 25 C, as we saw in the previous slide. If we use a flow cell, the ultrapure water does not pick up CO2 from the air. The conductivity should be near 0.055 microsiemens per centimeter at 25 C, or near 18.2 megohm centimeters resistivity. For example, if I use a flow cell with a conductivity probe, I can expect to see a reading similar to the ultrapure water display if I use an appropriate nonlinear ultrapure water temperature compensation on my meter. Alternately, I can make the readings without temperature compensation and compare to a table of calculated ultrapure water conductivity readings at various temperatures. Here's an example of conductivity measurement equipment. This is a Thermo Scientific Orion portable conductivity meter with a stainless steel conductivity probe and a glass flow cell, which comes with the stainless steel probe. I can use this equipment to make either a grab sample measurement or a flow cell measurement. Both tests are valid, just the results that we expect will be different. See your application note for details. Here we see an example of a flow cell measurement of ultrapure water conductivity. The ultrapure water flows into the bottom of the flow cell, past the conductivity probe, and out of the cell to drain. I have turned on the nonlinear temperature compensation for ultrapure water, and we are reading 0.055 microsiemens per centimeter. This is what we expect when there's no CO2 present and we're using a nonlinear temp comp for ultrapure water. In this case, my ultrapure water as dispensed looks good. Here, we see an example of a grab sample measurement of ultrapure water conductivity. The same ultrapure water as tested in the last picture is now collected in a beaker that I've rinsed 3 times with ultrapure water. Then I fill the beaker with water and take the measurement when the reading stabilizes. Notice that the reading is significantly higher, although I am measuring the same water. In this case, CO2 has been absorbed into the water, and the conductivity reading reflects that. Here also, my ultrapure water as dispensed looks good when compared to the USP 645 specification for a grab sample. My measured conductivity is well under 1.3 microsiemens per centimeter, which is the maximum allowed conductivity for the stage 1 specification. Let's consider some frequently asked questions about the pH of ultrapure water. Should I worry about a pH between 5 and 8 if I decide to test my ultrapure water? Well, probably not. As we've seen, a pH between 5 and 7 or 8 can be attributed to innocuous exposure to CO2 in the air. In addition, pH is not considered a useful indicator of ultrapure water quality because of the expected CO2 absorption. Will this pH difference affect a solution that I prepare with ultrapure water? In most cases, we don't expect there to be a significant effect. CO2 will be present in any solution that we prepare in an air atmosphere. In general, it may be more useful to monitor control the pH of the prepared solution than the pH of the ultrapure water used to make the solution. There are exceptions, for example, a recipe that calls for CO2-free water. Do I need to adjust the pH of ultrapure water before I use it? Again, in most cases, you don't expect there is a need to adjust the pH. While the pH may be noticeably different than 7, the acidity of ultrapure water is negligible. This is not a highly buffered sample. So, for example, if I have 100 mL of ultrapure water at pH 5.7 and I want to neutralize it to pH 7, I can titrate it with 0.02 molar sodium hydroxide. If I do that, it will take less than a drop of base to neutralize the water to pH 7. This shows how little acidity the CO2 adds to the ultrapure water. If I did add sodium hydroxide to fix the pH of my water, I would then have contaminated my water with sodium at around 180 parts per billion. This may not be desirable. Here's a slide that shows how the pH and the acidity of ultrapure water compare to the pH and acidity of an acetate buffer. Note that the pH of the ultrapure water and the acetate buffer are very similar, but acidities and buffer capacities are very different. In the case of ultrapure water, it will take only 0.04 mils, barely a drop, to neutralize 100 mils to pH 7, while it would take 46 mils to neutralize 100 mils of acetate buffer. That's a factor of more than 1,000 times difference. So, even though the pH values of these two samples are very similar, the acidity of ultrapure water is very different than the acidity of the acetate buffer. The acidity of ultrapure water is minimal, even though the pH reading might at first glance make us think otherwise. Here are 5 reasons to not use pH as our ultrapure water quality indicator. Number 1. Experts and standard organizations agree pH is not a useful indicator of ultrapure water quality. 2. pH of ultrapure water is challenging to read accurately. 3. The pH of ultrapure water changes due to CO2 absorption. 4. Ultrapure water is an unbuffered liquid. A minute amount of CO2 absorbed will cause a deceptively large pH change. And 5. Ultrapure water at pH less than 7 is not significantly acidic. When we want to know ultrapure water quality, instead, we may be wanting to look at conductivity, TOC, microbial measures, etc. So, if we really do need to test the pH of ultrapure water, how do we do it? As we know, pH measurements of ultrapure water are challenging. However, if we add a small amount of a neutral salt to the sample, it will stabilize the reading. It will not significantly affect the pH. A good pH electrode will help reduce noise and drift and increase accuracy. See our application note for some more information. Now, let's move to our second survey question.
Thank you, Gayle. Using the survey question module in the center of the screen, please answer the following question. What impurities are critical to your lab testing? Check all that apply. Just a quick reminder, if you have any questions, you can enter those using the Q&A module in the lower right corner of the screen. I'm going to give it another moment because it looks like answers are still coming in. All right, I'm going to share the results and we're going to have Kim Knepper explain the results.
Thank you, Lauren. So I see that ions, organics, and bacteria are the top impurities that are critical to your lab work, while nucleases and endotoxins are there also in particulates. But it looks like ions, organics, and bacteria are definitely a concern for most of your labs. So let's go ahead and look at the third myth of measuring ultrapure water. So the third myth of ultrapure water is the ultrapure water system display will measure all of the impurities in the water. Now sometimes the expectation in the lab is that the display tells the story about all the parameters that are important to the lab. This includes pH, ions, organics, bacteria, particles, endotoxins, and even nucleases. But ever notice how the ultrapure water system will only display resistivity, conductivity, or even possibly total organic carbon? Some impurities are easily measured on the water system and monitored by the display, while other impurities do not show up in the display at all. So next, we're going to answer the questions, what impurities can be measured by the water system? And if some impurities are not measured, how do we even know that they are there? So it's often assumed that the purity display on the water system is also related to the pH. And as we heard earlier in the presentation, pH is simply not a measurement of pure water. Ultrapure water systems remove impurities from the water to trace levels, but it cannot guarantee a specific pH level for the water coming out of the system because of the lack of ions in the water and because of the absorption of CO2. The ASTM standard specification for reagent water, D1193, establishes water quality standards for the lab use and will not even list pH readings for type 1, 2, or type 3 water. ASTM defines water purity based primarily on resistivity and total organic carbon. In fact, ASTM doesn't even list pH until type 4 quality, which is 5 microsiemens or 0.2 megohms. Per ASTM, quote, pH at 25 degrees Celsius is not applicable to higher resistivity waters. So positive and negatively charged ions in the water are easily measured by ultrapure water systems and monitored by the digital display. Note, these readings are taken in the water line when the system is recirculating the water and right before it is being dispensed from the water system. And that is exactly where ASTM defines where the readings should be taken. Their inline readings. Now, one question that is often asked is the resistivity or conductivity display measuring the total ionized solids or the total dissolved solids? The total ionized solids are calculated by the resistivity or conductivity of the water, and it's the number of ions in the water that can carry an electrical current. The total dissolved solids may include other impurities dissolved in the water, such as organics and colloids, in addition to the ions. So this is actually measured gravimetrically. So the resistivity or conductivity display on the ultrapure water system is only measuring the total ion content of the water, or the TIS. Now, organics in the water, the monitoring and display of the total organic carbon content in ultrapure water is becoming increasingly important as biomedical methods become more sensitive to low levels of organics. And in addition to visualizing the resistivity of the ultrapure water, a lot of you may want to quantify the amount of organic impurities in the water. Organic-free water is critical to applications that are sensitive to organics, such as HPLC and GCMS. So it's imperative that the TOC measurement be monitored for accuracy to prevent negative results. So the TOC can be measured in the ultrapure water system, but only if we change the organic chains into ions. Now, how do we do that? Water systems that use a dual wavelength UV bulb recirculate the water past the bulb to expose it to the ultraviolet light. The water system measures the overall water, the product water quality, the conductivity, and the water circulates past the UV bulb. The UV light oxidizes the organic compounds in the water into CO2 and water. The CO2 that is created is able to be measured by the downstream conductivity cell, as noted as C2 in this drawing. The amount of extra ions in the water is directly proportionate to the amount of organics in the water if the UV bulb is working. So the difference between the product water conductivity and the TOC conductivity is calculated, and we are able to see a TOC value, and that can be displayed. The accuracy of the TOC measurement depends on how well that UV bulb is irradiating the water. If the bulb is not fully illuminated, the total amount of organics in the water will not be oxidized, resulting in a false reading. So to protect against this, Thermo scientific engineers created a photoelectrode that directly monitors the UV lamp and ensures that it is working properly. So if there is a problem, the system is designed to display an error. Will the Ultrapure Water system display show if bacteria is present in the water? Unfortunately, no. Bacteria in the water is not measured by resistivity or conductivity, or necessarily indicated by the TOC. So even if the TOC level is elevated because of the bacteria metabolites, it would not be able to quantify or identify this as specifically bacteria. So, and even though bacteria is not measured, bacteria is certainly a concern because it can create problems such as plugging filters, or it could even coat the inside of the water system with a biofilm, including the conductivity cell, and prevent it from measuring the trace ions in the water. So bacteria in the water system is usually, it has to be measured outside of the system, and it's measured by a heterotrophic plate count, which actually counts the number of colonies formed by bacteria in a specific sample of water. So because bacteria cannot be measured by the water system, maintenance such as regular disinfection, cartridge, filter, and UV light replacements, these are going to be key to making sure that bacteria in the system is kept to a minimum. So the truth is the system cannot alert the lab if the bacteria is growing in the system. Prevention is definitely going to be key. The particulates in the water are not ionized and therefore not measurable by the Ultrapure Water system. Now, particulates can cause problems by plugging filters and cartridges and creating wear and tear on pumps and valves. These can either be visible to the naked eye, for instance, rust or algae as shown here, or they could be submicron in size. Particulates can be measured outside of the water system with turbidity meters. And turbidity meters measure the amount of light that is scattered by the debris in the water, so debris like the sediment, rust, and even bacteria. So in most applications, turbidity can be measured to determine its suitability for maybe feeding a water system, such as a reverse osmosis system. High turbidity may indicate that additional filters may be necessary. So particles are another impurity that is not measured by the Ultrapure Water system conductivity or resistivity display. And then finally, the Ultrapure Water system will not measure or display if endotoxins or nucleases are present in the system. These impurities often come from bacteria, so if bacteria is present in the system, these are likely to found in the system as well. Endotoxins are pieces of gram-negative bacteria that will interfere with the growth of mammalian tissues and cells. Nucleases include the enzymes RNase and DNase, and they break down RNA and DNA. So testing for these contaminants would require special test procedures and handling to prevent contamination and inaccurate results. So for example, shown here is a gel with an ethidium bromide stain, and lanes 7 to 14 show the presence of RNA in the sample, which indicates that the contaminant RNase enzyme was not present in the Ultrapure Water sample that was tested. So that brings us to the next survey question.
Thank you, Kim. Using the survey question module in the center of the screen, please answer the following question. Does your Ultrapure water system contain any of the following? Check all that apply. Just a quick reminder, if you have any questions, you can enter those using the Q&A module in the lower right corner of your screen. I'm going to give it another moment as the answers are still coming in. Okay, I will now share the results and hand things back over to Kim.
Thanks, Lauren. So I see a lot of you have individual cartridges in your water system and UV lights and ultrafilters. And about half of you have a point-of-use final filter. So we'll be talking about some of these different additions to the water system and how they affect the water. So let's dive right in and talk about the fourth myth. Accessories added to the Ultrapure water system will always improve conductivity or resistivity. So these accessories could include the cartridges, UV light, ultrafiltration, point-of-use final filter, or even additional tubing. So the truth is yes and no. It depends on how and where it is added to the system. So let's talk about water purity and what can interfere with the water system's ability to achieve and maintain 18.2. The order of the cartridges and the components are very important. The high precision purity sensor is very sensitive and it's designed to measure very small changes in purity. So remember, we're dealing with trace levels of impurities. The purity sensor in the water system is strategically placed right before the dispenser, and that way you are sure of the water quality as it's being dispensed. Ultrapure water systems use cartridges that contain different resins that need to be installed in a specific order. So the cartridge combinations are optimized to remove a range of impurities in the water, including those that are not quite so measurable, those organics that could be in the water or the colloids. So often that first step is some type of pretreatment to prepare the water for those final stages of the trace ion and trace organic removal. So if you have individual bowl type cartridge systems with the individual cartridges, installing the cartridges in the system out of order can definitely interfere with the system's ability to achieve high purity water. And note, when these cartridges are newly installed, often it does require maybe a rinse up and a recirculation period to achieve their highest purity. Accessories added to the water system, such as the UV light, can definitely affect the purity. The dual wavelength UV bulb is especially selected to break down organic compounds in the water into CO2 and water. And carbon dioxide could be measured by the purity sensor. UV lights are not only effective at killing bacteria and breaking down organics, but it also releases any ions that could be attached to the organic compounds. Because these additional ions in the CO2 are easily measured by the conductivity cell in the system, the UV lights are strategically placed before the final DI cartridge, so any byproducts from the oxidation process can be removed. So in some cases, customers ask about adding a UV light accessory to their existing system. Just note if they are added outside of the water system, considerations need to be made about how they could affect that overall water purity because of the breakdown of organics and bacteria. So accessories within the water system is best, but always double check with the manufacturer before adding anything to the water system. Ultrapure water systems use a point-of-use final filter, and it's installed right at the point of dispensing to filter the water for any bacteria or particulates. Now often this is an absolute 0.2 micron in size. So since these filters are often outside of the recirculation loop, they're exposed to the atmosphere. And they're subject to picking up any contaminants from the atmosphere, including bacteria, organics, or ions, or ionized gases. So rinsing that final filter before sampling is a very good practice. Point-of-use Type 1 Ultrapure water systems with an ultrafilter are designed with a much smaller pore size than a final filter. So it's designed to remove parts of bacteria, such as endotoxins or nucleases. Ultrafilters can be inline, or they could be at point of use. So inline ultrafilters have the advantage of being in the recirculation loop, not exposed to potential airborne contaminants. and they often have the advantage of a cross-flow rinsing of the ultrafilter surface to prevent any buildup of impurities. And this would ensure a longer life of the inline ultrafilter versus a point-of-use ultrafilter. Now, these filters do have a large surface area, so they may need some rinse-up time when the ultrafilter is new to flush the surfaces and to remove any trapped air. Ultrafilters that are built into the thermoscientific water systems are one of the last components the water will flow through before it is dispensed. Therefore, it allows the user to see the actual water quality of the entire system. So if the ultrafilter would be added externally, it could be subject to the contamination of the atmosphere, like the final filter. Purified water systems often recirculate the water throughout the system to maintain the high resistivity purity of the water. When there are periods of non-use, such as at night or long periods of time throughout the day, if the system's not being used, the system may be put into an interval or maybe a standby mode. And when this happens, the recirculation pump will move the water around the system for a period of time, and then it will rest. So what happens to that water purity when the system is resting? The water resistivity will slowly drop, or the conductivity will slowly rise, as small amounts of ions could be picked up, or maybe a reverse exchange could happen from the DI resin. So the last component of the recirculation path is the final conductivity sensor to measure the water purity as it's being dispensed. If the water is not being dispensed, it's recirculating all the way back to the beginning again for more polishing. So you can see in this drawing, this type 1 water system has a complete recirculation loop of that full water pathway from the first stage of purification to the dispenser. So a common question we get is, should I turn my water system off at night or on the weekend? It would be recommended to keep the unit on and put it in a standby or an interval mode, so that way the system is able to purify the water quickly when the lab does need the water, and it would also help discourage any bacterial growth. Now, once the water has left the system, it is out of the recirculation loop, and it's subject to any changes in the purity based on the environmental conditions or anything it would be in contact with. So if there's additional tubing or accessories, it could pick up impurities from that. So adding any components outside of the system, especially those that are not standard from the manufacturer, it would need to be evaluated to determine the risk of potential contamination of the water and how that could impact the lab work. So what happens in water systems that do not circulate the water? And this would be common in a service DI water system that's feeding a building with high purity water. And these systems are a dead leg, and the water purity will stagnate and the purity will be reduced while the system is sitting idle. And because of this, there's the potential for bacterial growth or impurities that could be picked up along the way from the piping. So today, we busted some myths about ultrapure water purity measurements of conductivity and pH. So myth number 1, the ultrapure water conductivity after dispensing should match ultrapure water system display. The truth is the water will pick up CO2 from the air. However, the water will be considered pure, and that CO2 can be accounted for. Myth number 2, the pH of the water should be exactly 7.0. But the truth is, the pH that can quickly decrease after the ultrapure water has been dispensed. pH, as we have seen, is not a measurement of pure water. And even if the pH is low, the buffer capacity of the water is very low. Again, it may be more useful to monitor and control the pH of the prepared solution than the pH of the ultrapure water that's used in making that solution. Myth number 3, ultrapure water system display measures all impurities in the water, but as we have seen, some impurities are easily measured while others are not. So it's good to be aware of anything additional if any additional monitoring or testing would be required. And then myth number 4, accessories added to the water system will always improve conductivity or resistivity. Always check with the manufacturer before adding any additional accessories, as they may change the water quality. Exposing these myths and the truth of the ultrapure water, measurements of conductivity and pH will lead to improved testing and understanding of your results. So as we come to the question and answer portion of today's presentation, I'd like to point out to please be sure to visit our resource center at thermoscientific.com/water and thermoscientific.com/purewater to view our complete water line and to have access to our product videos, brochures, application notes, and presentations.
Thank you, Kim. It looks like we've received several questions for our water experts, and of course, keep them coming. Before we get to those, though, I'd like to draw everyone's attention to some links now on your screen. The first is an attendee survey found in the lower left corner. Let us know what you thought about today's session and suggest future webinar topics. Also, at the bottom of the screen, we've included several resources related to today's discussion. We encourage you to download those for future reference. All right, that's enough from me. Let's dive into some of our questions. Our first question asks, when I check the pH of the reverse osmosis water, I get a pretty accurate reading, but when I check the type 1 deionized water, I get a drifting pH. Why does this happen? Gayle or Kim?
Hi, Lauren. I can take that one. Yes, this can happen. Type 1 water is high resistivity water, as we've just been talking about. So this high resistivity interferes with pH measurement, which relies on the sample itself to complete part of the measuring circuit, and there's other effects due to this high resistivity. These effects can lead to issues such as noise, drift, non-reproducible readings, and or bias. But in contrast, we can expect RO water to have more ions and a higher ionic strength. The higher ionic strength sample will allow for a reading that's less noisy, more stable, faster, more reproducible, more accurate. It will be easier. So that kind of explains why you may see a drift in pH when you're measuring ultrapure water.
Great, thank you, Gayle. I have another question. Looks like this is for Kim. Does hollow fiber reduce the quality of the water when it does pass through?
So the final filter, does it affect the purity? So when the final filter is outside of the recirculation loop, so the first thing I would recommend is rinsing at least 500 mLs of water through the filter to eliminate any possible airborne contaminants that could have settled on it. And it will flood the filter with water. Now, the final filters are especially picked for their inert qualities and that they will not slough off any impurities into the water. So I don't expect that the resistivity will drop a lot at that point. However, as soon as that water does get exposed to air, it will immediately absorb carbon dioxide. To prevent any more changes in the purity, make sure there's not a lot of splashing of the water as it's being dispensed and introducing any air into the sample.
Great, thank you, Kim. Next question, how quickly does conductivity increase when exposed to air? Gayle or Kim?
Sure, I can talk to that a bit. It's really fast. When I'm training people on how to measure conductivity of ultrapure water, we have this sort of comparison that we do. We have people measure the conductivity with a flow cell, and we read, let's say, 0.055, just as we expect it to read. And then we take the same water, put it in a beaker, a clean beaker, and put our dip type probe in. And it's immediately at least twice that, and then often goes up and settles somewhere around 0.3, 0.4, 0.5 microsiemens per centimeter. So the effect is really quite quick. It pretty much dissolves into the water right away.
Thank you, Gayle. Our next question, is ASTM type 3 above 4 megaohms per centimeter?
I can speak to that. The last time I looked at ASTM D1193, the specification for type 3 water is for a minimum of 4 megohm centimeters per the water. But just to be sure, you should consult your latest copy of your ASTM D1193 reagent water standard.
Thank you. Our next question, why for environmental chambers, incubators, and water baths do they often say to use distilled water? What is the difference in purity in distilled versus deionized water? Gayle or Kim?
I'll take that. So distilled water and deionized water are both high quality water. Now the difference between that is the deionized water, often when it's freshly made, the water is quite aggressive and unstable. And as we have talked about today, it will readily absorb anything it can back into it. So first thing it likes to absorb is carbon dioxide from the air. But if I take this water and put it into any container, like a metal container like a water bath, or put it into an incubator, it will actually try to pick up ions from the metal and could degrade the coating on the water bath or the incubator. Distilled water tends to be a little more stable because it's made slowly over time, and it has more contact time with the atmosphere to equilibrate and to be less aggressive.
Thank you, Kim. Next question. It's about conductivity again. How is the conductivity of softened water different than the conductivity of DI water? Gayle or Kim?
I can answer that one. So softened water is basically, it's an ion exchange. However, it's exchanging hard ions like calcium and magnesium for softer ions of sodium. Because of this, the number of ions in the softened water and the conductivity of and the number of ions in the tap water are going to essentially be the same. Now, deionization is actually exchanging the cations in the water for H ions and the anions for OH ions, and that would be a complete removal of the impurities in the water. So the conductivity of DI water tends to be very low in compared to softened water, which, again, softened water is going to look much like tap water.
Thanks. Our next question, if I don't have a flow cell but want to check the display of my Ultrapure water system, is this even possible?
I can answer that one. Yes, there's at least two options that I can think of. One is I can collect a grab sample and measure it immediately. Then compare the results to the USP 645 specifications, since those specifications take into account the effect of CO2 absorption. The other option that I can think of is to make a pseudo flow cell by connecting tubing to the Ultrapure water outlet and placing a large beaker, say 400 or 1,000 mils in the sink. I need to make sure that the tubing and the beaker are clean and well rinsed with Ultrapure water before I start. If I turn on Ultrapure water and place the tubing into the beaker, then allow the Ultrapure water to flow, it will fill the beaker and overflow into the sink. I want to make sure the flow is not so fast to introduce air bubbles. If I then place my well-rinsed conductivity probe into the bottom of the beaker far from the surface of the liquid while the Ultrapure water continues to flow, and then wait for a stable reading. That reading will not be expected to exactly match the display, but it should be closer to the display than a grab sample. And when I've done that, I generally get within a factor of 2 of what I'm expecting. And so far I've always got less than 0.1 microsiemens per centimeter. So there are some options there.
Great. Big thanks to Kim and Gayle and all of our attendees for joining us for today's webinar. If you have any other questions, if we didn't get to your question, please feel free to forward those directly to Kim or Gayle at the email addresses shown on your screen. As a reminder, as a registered guest, you will receive an email within the next few days with a link to the recorded webinar. We encourage you to visit thermoscientific.com/lab water source for future webinar details and to access our library of recorded on-demand sessions. Thank you so much, and everyone have a great day.